Welcome to Lacea class. I am your teacher, John Lacea.
A blessed day to everyone! Today, we are going to learn the equivalent loops in 32-bit Windows assembly language. I have learned assembly language programming way back when I was second-year college student studying BS in computer science. I have taught this subject to some of my batches of BSIT students. Learning a second programming language is easier than the first because most programming languages have similar syntaxes, semantics, execution flow, and logic. So, why study assembly language? The assembly language allows us to learn internally how a CPU, memory, I/O devices, and operating system runs a software. Those who are proficient in assembly language are black wizards. Assembly language is used to write computer viruses back in the day, and it is a tool to hack a system. You are exactly close to the machine when you apply assembly language programming, and you can see binary numbers being processed, just like the movie The Matrix. Assembly language and combined with C language are used to develop operating systems such as Windows, Linux, Android OS, iOS, and so on. Assembly language and combined with C language are used to develop device drivers. Finally, assembly language is used to develop optimized machine execution for computation, computer graphics, microcontroller libraries, and so on. In order to learn the equivalent loop statements in assembly language, let us learn first the two types of jump machine instructions, such as the conditional jump instructions and the unconditional jump instruction. There are multitude of instructions that you can use to influence the control flow of a program. Most of these instructions are conditional jump instructions. Normally, the processor executes instructions one after another. A jump is an instruction that tells the processor to continue execution at the given address, which is particularly a label. Assign a label name. In effect, control is transferred to the first instruction following the label. So the CPU can jump like a frog. One type of jump machine instructions is the unconditional jump instruction, which is the mnemonic symbol command GMP. This example code, which is a assembly language code, has a written label named L1 with a colon. That is the syntax on how to write a label, how to place a label in our assembly language code. When the assembler will compile this label, it will definitely assign a memory address. And then that label will become a memory address so that our unconditional jump instruction, GMP, can jump to that memory address. When the CPU executes the command GMP at L1, the CPU jumps to the label L1 like a frog. Thus, the following lines of codes such as move AX 0, move BX AX are skipped. And then the following lines of codes are executed by the CPU when the CPU jump to the memory address given a label name L1, the following: move AX, num1, add num2, AX. Note that label names must be unique and it must not be duplicated. The assembler does not allow duplicate label names. Implementing jumps based on two numeric values is a two-step process. First, you compare the two values, then you perform a conditional jump based on the outcome of the comparison. To compare two values, we use this machine instruction, which is a mnemonic symbol, CMP. And then the syntax is, we write the mnemonic symbol command, CMP, followed by a first operand separated by a comma with a second operand. Here are descriptions of the various types of comparisons that you can perform. Each description is followed by an example. The CMP command, we can compare a register with a second register. For example, compare EX, BX. Note that when we compare two operands, they must have the same size or length. Here in this case, AX and BX are the same size, which is 16 bits. Another way to compare is that we can compare a register with a memory variable or a data item. For example, compare AX with that memory variable declared total. As long as this variable total is declared as a defined word, which is a 16-bit, it will successfully compare with that 16-bit register AX. Next, we can compare a register with an immediate operand like a constant number. For example, compare EX with a value 0. Next, we can compare a memory address or a data item with the register. For example, compare the memory address total with that register AX. Finally, we can compare a memory address with an immediate operand or a constant value. For example, compare a memory variable with that constant value 0. You cannot compare two data items or memory variables directly. If you need to compare two memory variables, you will have to copy one to a register first. For example, if we declared two memory variables of the same sizes, num1 and num2, and then we write it this way using compare CMP, it will not be valid. It will generate a syntax error. The proper way is we need to copy the value of one memory variable to a register with the same size. For example, in this example, move AX num1 and then followed by compare EX with the value of that memory variable num2. When using compare CMP, both operands must be of the same length or size. Here in this example, compare EAX with BX will generate a syntax error because both of these two registers are not the same in size. EAX is a 32-bit register while BX is a 16-bit register. The following two lines of codes are correct, such as compare EAX with EBX, compare EX with BX. After a CMP or compare instruction, you normally use a conditional jump instruction to test the results of the comparison. Memorize or familiarize the following abbreviation to use for the different conditional jumps. The abbreviation N stands for not, E stands for equal, G stands for greater than, L stands for less than, B stands for below, and A stands for above. The processor has two sets of conditional jumps that you can use after a comparison using the CMP. The two sets are similar. The only difference is that one set is for signed numbers or positive and negative numbers, while the other is for positive numbers or unsigned numbers only. Here are conditional machine jump instructions that are used for signed numbers. One is the GL unconditional jump. One is GL, which is the conditional jump. And then the meaning of that is that if the condition satisfied, it will jump to the particular label assigned if it is less than. If the comparison is less than. GG stands for jump if greater than. GLE stands for jump if less than or equal to. GGE stands for jump if greater than or equal to. GE stands for jump if equal, while GNE stands for jump if not equal. Assembly language does not allows us to use those relational operators that we used to use when writing a condition in high-level programming languages. Instead, we need to use these mnemonic machine instruction commands to perform a conditional jump. The following set of conditional machine instruction jumps are for the positive numbers or unsigned numbers. One is the GB, that stands for jump if below. GA stands for jump if above. GBE stands for jump if below or equal to. GAE stands for jump if above or equal to. GE stands for jump if equal to. And then finally, GNE stands for jump if not equal to. We use this if our comparison, the two operands that we are comparing to using the CMP command contains positive numbers only. When comparing two operands, you must pay attention to the order because it does matter. For example, we have two memory variables declared, A and B. The first example here, written in assembly language, will have a order of how we compare the memory variables A and B. For example, move EAX, the value of B, and then followed by compare A with that value of that register EAX. And then we write the next command, jump if below to L1. Therefore, when we try to understand the compare of A to that register and note that this EAX contains the value of B, and then we use GB for conditional jump. Therefore, it means that if A less than B, and if it is true, then jump to L1. So the order will now be A will now be the first operand followed by less than and then followed by the second operand, which is the variable B. If we want to perform the opposite, we can do it this way. This second assembly language code will give us a way to perform a comparison, which is the opposite. Move EAX, the value of A, compare B with that value of EAX, and then followed by jump if less than to L1. And since the value of EAX contains the value of A, and then in our comparison using compare, we write first the first operand, which is the memory variable B. Therefore, the order will now be if B less than A, and if it is true, then jump to L1. Although the assembly language has machine instruction, loop, loop E or loop Z, loop NE or loop NZ, but it has no built-in structured loop statements compared to high-level programming languages such as Java, C#, Visual Basic, Python, and so on. Therefore, we need to create a code template to mimic a loop statement. Let us now learn the code template for the for loop statement. These assembly language codes are equivalent to this C, C++, Java structured for loop statement. So let us convert this into a equivalent machine language, machine assembly language equivalent. The machine instructions such as the loop, loop E or loop Z, and loop NE or loop NZ assign the register ECX or CX as the control or sentinel variable. Thus, we cannot use other register except the ECX or CX register. Every time the for loop repeats, it will subtract 1 from the present value of that ECX register. So, take a look at this equivalent code written in assembly language, a for loop. So, we assume that we declare a memory variable n, and then that memory variable n contains a numeric value. In fact, we can replace that n with a exact numeric value on how we wanted to program the code to repeat. Whatever the value of n, whether it is 5 or 3, that dictates this code that it will repeat. So, we need to use the ECX register because that is the permanent fix assign when we use this different machine instruction loop, loop E, loop Z, loop NE, or loop NZ. So, we write this code, move ECX, with that value of that memory variable n or any numeric value. And then afterwards, we assign a label name and I name it for loop with a colon. And then after that, this will now provide us the body of the for loop that it will be repeated to be executed by the CPU. When we go inside the body of the for loop, we need to push the value of that ECX. And then later on, we pop the value of that ECX when we are done with our code inside the body of the for loop so that we can preserve the contents of that ECX. If in case we use that register ECX, the accumulator register inside the body of our for loop, we need to preserve that inside the memory of the computer. The computer has a stock memory as a temporary data storage to preserve not only registers but also local variables entering a procedure or a function. So the next command is push the value of the ECX into the stock memory, the last in, first out data structure memory. And then after that, we can now write our code that it will be repeatedly be executed by the CPU, and we can use the ECX as a register to hold some values. At the end of our body, we pop up the value of that ECX to return back the previous contents when we push it to the stack memory, so that the loop command, which is this loop followed by the name of the label for loop, will going to run properly. So that loop command here will going to deduct or subtract a 1 to the current value of that ECX. And then this loop will repeat again, jumping to that label for loop if the value of that ECX is not equal to 0. It will going to repeat, jumping to this label, repeated a couple of times, as long as the present value of that ECX is not equal to 0. By the time that the value of this ECX becomes 0, that's the time that it will stop repeating the loop. The loop E or loop if equal to 0, another equivalent command to that is the loop Z, which is a variation of that loop mnemonic symbol machine instruction. But the logic that it will repeat is that it will only repeat the loop if the present value of that ECX is equal to 0, which is opposite of that loop. And then the third one, which is loop not equal to 0 or loop NZ, it will repeat the value of the loop if the present value of this ECX is not equal to 0. And then this loop and loop NE or loop NZ are the same in logic. The same the way how they repeat with such condition. To this third column, when we use the loop command, it does not affect the flag register. But if we use the loop E, the flag register ZF will contain a value of 1 every time that the present value of that ECX is 0. When we use the loop NE or loop NZ, the value of the register ZF will be 0 every time that this ECX contains a non-zero value. Let us convert this C for loop statement that it is programmed to repeat 5 times, and it will display the message hello world 5 times using the assembly language machine instruction loop. First and foremost, I declared some memory variables to the data segment. I declared a string named message assigned with a byte data type, and then it contains an array of characters, hello world, that ends with a integer 0, and that is needed for the print user-defined command that I program. Next memory variable is the new line, that the purpose of this is that whenever we print this memory variable new line, the blinking cursor will move to the next line. And then it contains an array of integer numbers, the numbers 13, 10, and 0. 13 is a ASCII code for enter key, whereas the ASCII code 10 is a new line, which is the equivalent of this in C++ Java. /n is the ASCII code of 13, and then /r, the carriage return. The carriage return is the ASCII code 10. Another memory variable that I declared is the str value, that the purpose of this is it will store here the converted integer number into a string. This str value contains an array of 30 spaces, and it ends with a integer 0. Let us proceed to the code segment, and then we have now the code that will going to repeat 5 times, and it will print hello world 5 times on the monitor screen. So the first thing that we do is to move ECX with a value, with the value of a constant integer 5, and it will dictate that this loop command will going to repeat 5 times. And again, I name the label for loop with the column that the loop for loop will going to jump here as long as the present value of that ECX is not yet equal to 0. Inside the body of this for loop, we need first to preserve the contents of the ECX, and then after that, we call the user-defined function integer to string. We will going to convert the present value of that ECX into a string, store to that str value, and then after that, we print that str value. And then since the value of that ECX contains 5, it will print the character 5 onto the console window, followed by print MSG or message hello world, and then followed by print new line 1310, so that the cursor, the blinking cursor, will be blinking to the next line in preparation for the next message to be displayed. After that, the pop ECX will be run by the CPU, and then that ECX that contains the original value of 5 will now be restored to that ECX, and it contains now 5. And then this loop command will going to deduct 1 to the present value of that ECX, so 5 minus 1 will now become 4. And then before it will jump to that label for loop, it will first compare, is the present value of that ECX not equal to 0? Since the present value, which is 4, not yet equal to 0, it is true. Therefore, the CPU will going to jump from this label and then repeat again. So, when the CPU will going to execute this following for loop equivalent written in assembly language, it will display this following output messages onto the console window. This new example demonstrates the usage of the assembly language machine instruction loop E or loop Z, or repeat if the present value of that ECX equals to 0. So let us convert this following code written in C, C++, Java into a assembly language applying the loop E or the loop Z. The code is much similar with the previous code. The only difference is that I replaced the loop machine instruction jump command with loop E. So when we try to trace the first repetition, move ECX 5, the CPU now will move to the command push ECX. The value of that ECX 5 will be stored or pushed into the memory stack of the computer, and then followed by the next command. It will convert that 5 into a string, and it will store to that str value, and then it will print the value of that, which is 5, followed by print hello world, followed by print new line. So the blinking cursor will be blinking to the next line. And then followed by pop ECX, the present value now of ECX contains the value of 5. And then the CPU will going to execute that loop E. But the condition of this loop E is that if the present value of that ECX is equal to 0, it will going to jump to that label for loop. However, the present value of that ECX which is now, right now, a value now of 4 because the loop E command will subtract first E1 to the present value of that ECX 5. So it becomes now 4, and then after that, it will compare if it is equal to 0. And since it is false, it will not jump to that for loop. Therefore, this for loop statement will only repeats only once. And it will only display one hello world message onto the console window. The next example demonstrates the usage of the assembly language machine instruction loop NE or loop NZ, or repeat if the present value of ECX is not equal to 0. We learned a while ago that the loop and loop NE or loop NZ are the same. Therefore, when we execute this code, it will repeat 5 times, and it will display 5 hello world messages onto the console window. Take note that every time that this loop NE will going to repeat, it will deduct or subtract 1 automatically to the present value of that ECX. And then it will compare if the ECX is not equal to 0. By the time that the value of the ECX contains now a 0, therefore it will stop repeating. Let us learn the next type of loop statement, and the code setup written in assembly language contains now the equivalent of the while loop statement. This is the setup or the template for the equivalent while loop statement. So the first thing that we are going to do is to write first a label, name a label with a colon, and then we set up now the body of the while loop in this manner. And then in the body of the while loop, we can apply the compare command to compare two operands, followed by any conditional jump. And then if that conditional jump satisfies the comparison, it will jump to the label and while loop, which is this one, that it will now stop repeating the while loop. However, if the comparison does not satisfy the condition, it will not jump to that and while loop. Instead, it will move on to the next command, until it reaches the last command, which is the unconditional jump GMP to the label while loop. So this command GMP space while loop will jump to the label while loop without any condition, so that it will repeat the body of the while loop. Let us examine this assembly language codes that applies the template for the while loop statements. Let us convert these C++ codes that repeats 5 times using the while loop. First and foremost, we need to declare some memory variables. Under the data segment, I declared again the memory variable MSG that contains the message hello world, new line that contains 1310, array of integers, str value that contains an array of 30 spaces with a integer number of 0, used for integer to string conversion. And then the new memory variable that I declared here is the variable CTR, assigned as a double word DD and initialized to 0. The purpose of this variable CTR is that it will serve as the sentinel or the control variable for our while loop. Let us proceed to the code segment. So CTR is equal to 1 in C++, C# code. will now be the command move CTR1. We will initialize, we will change the value of that CTR with a 1. It will begin with a 1. And then after that, we write a label, we name a label while loop followed by a colon, and then the body of the loop are the following. We first compare if the present value of that CTR with the value 5. And then followed by a conditional jump. And then I choose the conditional jump GG. That stands for jump if greater than. We can also use the other command GA, jump if above. And then followed by the label and while loop. This and while loop is written at the end that indicates that if that GG satisfy the condition, therefore it will stop the while loop from repeating. However, if the GG conditional jump does not satisfy and it will not jump to that and while loop, the rest of the body of the loop will be run by the CPU, such as the following: integer to string. It will convert that present value of that CTR with containing 1 into a string value of 1, and then it will print it out onto the console window, the 1 value, followed by print message, hello world, followed by print new line. It will move the blinking cursor to the next line, and then the while loop, unlike the loop machine instruction command, that it will automatically deduct A1 to the present value of the ECX. Here in this case, we need to write our increment or decrement command that will change the value of our sentinel or control variable CTR. Here in this case, I wanted to increment the value of that CTR, and then there is a machine instruction set called INC, followed by a memory variable that will perform the deduction of A1, which is the equivalent of the machine instruction set command add CTR with 1. So the present value of CTR will now be added by A1, and it becomes now 2. So this control variable CTR contains 2, and then the next command is the unconditional jump GMP to that label while loop. So it will jump to that label while loop, and then next it will compare the value of CTR containing 2 with 5. Next command, GG, is the present value of CTR, which is 2 greater than 5, false. Therefore, it will repeat again the second repetition, and it will print 2 hello world. By the time that we reaches the value of CTR upon adding with a 1 value, and it becomes now a 6 value. For example, the present value of CTR now is 5 plus 1, it becomes now 6, and then this GMP while loop will jump to this label while loop, and then again we tell the CPU that we are going to compare the present value of CTR, which is 6, to that 5. The next command, GG, is 6 greater than 5. This time, it is true. Since it is true, the CPU will jump now to the label and while loop, and it will stop repeating now the loop. Here is another example of while loop statement equivalent in assembly language that repeats 5 times, but this time the control or sentinel variable CTR is subtracted by 1 every time that it repeats. Let us convert this C++ Java codes that repeats 5 times using the while loop. So instead of incrementing the present value of CTR, we instead decrement or subtract a 1 value. So the first thing that we are going to do is to initialize the control or sentinel value with a value of 5. So CTR now contains now a value of 5. Next, the CPU will execute the compare 5 with 1. And then the next is the conditional jump GL. Jump if less than to the label and while loop is 5 less than 1 and it is false. Therefore, it will not yet stop repeating. It will not yet jump to the label and while loop. So it will going to perform the rest of the body of the loop. It will convert the integer to string, and then it will print the value of 5, and then it will print the hello world, and then it will move the blinking cursor to the next line. And then again, it will deduct or subtract a 1 to the present value of CTR. 5 minus 1, it will now become 4, and then it will jump again to the label while loop. For example, the present value of CTR is now 1, and then we are about to call the command dec CTR. So CTR will now be 1 minus 1. It becomes now 0. So CTR now contains 0, and then jump to the label while loop. We compare 0 to 1. GL and while loop is 0 less than 1. This time it is true. Therefore, the CPU will jump to the label and while loop, and it will now stop repeating our while loop. Let us learn how to set up a nested for loop statement in assembly language. The way how I set up the assembly language codes is by first writing a sample nested loop written in C, C++, Java programming language, and then convert it into a assembly language equivalent. First and foremost, I declared some memory variables as usual. I declared message 1 that contains the string main loop, message 2 that contains the string subloop, new line that contains the array of integers 13, 10, 0, str value that contains an array of 30 spaces, and it then ends with a integer 0. We proceed to the code segment. I initialized the ECX containing 3 because I wanted to repeat the main loop 3 times. And then I assign a label for loop 1, and then the body of our main loop will now these following codes. And then again, we need to preserve the contents of the ECX before we run the code of our body of our main loop, and then followed by integer to string, print str value, print message 1, print new line. So it will display the message 3 main loop. And then the command move ECX 3, we are going to set up our subloop that it will also repeat 3 times. The body of our subloop will now begins with a label name for loop 2 with a colon. And then this is now the body of the main loop. Again, we need to preserve the register ECX into the stock memory of the computer, and then followed by integer to string, print str value, print message 2, print new line. So it will display 3 subloop, and then pop ECX. And then we wrote the command loop that it will automatically deduct 1 to the present value of the ECX, and then it will jump to that for loop 2 label if and only if the ECX is not yet equal to 0. So it will repeat 3 times. It will display 3 messages for sub loop. And when this sub loop stop repeating, that CPU will jump to this label for loop 2. That CPU will not anymore jump to that label for loop 2. Instead, it will now move to the next command, which is the part body of the main loop. It will now restore back the present value of ECX. And then, after that, we call the command loop followed by the label for loop 1. Before it will jump to that label, it will first deduct the 1 to the present value of that ECX, and then it will first compare if that ECX is not equal to 0. So 3 minus 1 is 2. Therefore, it is not yet equal to 0. So the CPU will jump to the label for loop 1, and again, it will repeat again our body of our main loop until such a time that it will now stop repeating. And when we run this code, it will now display the following messages onto the console window. The main critical point in setting a nested for loop statement is that we need to preserve the value of the register ECX so that it will perform the exact number of repetition for our main loop and as well as for our subloop. Failure to preserve the present value of our ECX register, it will cause a infinite loop that it will never stop repeating. Let us learn how to set up a nested while loop statement in assembly language. The way how I set up the assembly codes is by first writing a sample while loop written in C, C++, Java, and then convert it into a assembly language. First and foremost, I declared some memory variables to be used in our nested while loop statement. I declared a memory variable named row, assigned as a double word, initialized with a 0, and then this memory variable row will now be used as a sentinel or a control for our main while loop statement. Another variable I declared cool, assigned as a double word, initialized with a 0, is used for our sub while loop statement. That's the purpose of that cool. So in our C, C++ Java equivalent, our while loop is programmed to repeat 3 times, where our sub loop is programmed to repeat 3 times as well. So first, let us go to our code segment. We will initialize our sentinel variable row with a 1 with the starting value of 1. And then I wrote a label while loop 1. And then the body of our main while loop contains now the following codes. Next, we compare the present value of row containing 1 if containing 1 to that integer value 3. Next to that, I use the conditional jump if greater than to the n while loop 1. Jump if it is greater than to the n while loop 1. So we are trying to compare is 1 greater than 1, greater than 3. And it is false. So it will not yet stop repeating our main sub loop. Next, it will perform the rest of our body of our loop. It will convert integer to string, the present value of that sentinel variable row, and then print it out containing now 1 onto our console window. Next, it will print the value of that message 1, main loop, followed by print new line. It will move the blinking cursor to the next line, and then next to that, we increment or we add a 1 to the present variable row. So 1 plus 1, it will now become 2. And then the following code will now be the setup for our sub loop move cool with a value of 1. So we initialize the sentinel variable cool for our sub loop with a 1, and then we write a label while loop 2, and then the body of the sub loop while contains the following: compare the present value of the sentinel variable cool with 3, jump if greater than 2n while loop 2, which is this label. Is 1 greater than 3 false, it will not yet jump to that n while loop 2. It will convert that integer to string, the variable cool, print it onto the console window, which is 1. Next, it will print the message to sub loop. Next, it will move the blinking cursor to the next line, and then we add a 1 to the present value of that cool. And then we execute the unconditional jump GMP to the while loop 2 label. So this while loop sub loop will going to repeat 3 times. When this sub loop finish repeating 3 times, the CPU will move to the next command, which is the unconditional jump GMP while loop 1, and the CPU will jump again to the beginning start of our main loop, the label while loop 1, and again it will compare the present value of row containing 2 with that 3, and then jump if it is greater than to that label and while loop. And if we execute this code, it will repeat the main loop 3 times, and then every time that it will repeat the main loop, it will repeat the sub loop 3 times. I provided the following files written in assembly language to compile, run, and test. The following files are the following: for .asm, while.asm, nested for.asm, nested while.asm, and then local variable.asm. Let us open up the file for .asm using the Notepad 2 text editor. So I highlight and right-click that file and then open with Notepad 2. This is the actual code for the code that I explained, the equivalent of for loop in assembly language. Let us run this code. I click the file menu and then go to that go to this menu item, launch, and then select the command. We can also press the keyboard shortcut Ctrl+R, and then we type this command, M space the name of the file without any file extension, and then hit the enter key or click the OK button to compile, run, and test. So this for loop will going to repeat 5 times, and then it will display the messages hello world onto this console window. Let us open up the next file. I will open up the file while.asm using the Notepad 2 text editor. And then this is the code equivalent for the while loop that will repeat 5 times. So let us run this. I press the keyboard shortcut Ctrl+R, and then type the command M space the file without any file extension, and then hit the enter key. And then the output of that equivalent while loop statement in assembly language will display the messages hello world 5 times onto this console window. Let us close this and then open up the next file. Let us open up the file nested4.asm. This is the sample code that I explain how to write a nested for loop in assembly language. So let us run this. The main loop will repeat 3 times, whereas the sub loop will repeat 3 times. A total repetition of 3 times 3, which is 9 times. Let us move to the next file. Let us open up the file nested while.asm. This is the equivalent nested while loop written in assembly language. Let us compile, run, and test. The main loop is programmed to repeat 3 times, while the sub loop is programmed to repeat 3 times. So, all in all, the loop will going to repeat 3 times 3, which is 9. There is a special file that I provided, which is the file name local variable.asm. Let us open up this file. Although I did not discuss in the previous lecture, but I can tell you the purpose of this file. We can declare a local variable inside a procedure using this command, local, and then you name the variable. Here I baptize it with CTR, and then to assign a data type, I place a colon and then the data type the word. And then the following code here is a while loop that uses the local variable CTR as a control or sentinel variable. And if we run this file, but before we run this, procedure name repeat 5 times will be called here inside the main procedure of our assembly program. So let us run this. So the procedure repeat 5 times will repeat the while loop 5 times. I have provided a example laboratory hands-on exercise for you to solve if you are interested, applying the loop statements equivalent in assembly language. Try to solve this problem that you will apply the loop statement. I prepared 2 problems for you to solve. This is the second problem. Try to read and understand the requirements and then write the code in assembly language.
That ends our topic for today. I hope you are inspired in my class. Thank you for watching. God bless us.